Hello, I'm Dave Terry, also known as Troop to everyone, and we're here today to talk about the DC training panel. This is part of the apprentice electrician's training to preparing for the West Virginia electrical certification test. I'm going to take a few moments and identify the various components on the panel and point to the print to show you what symbols mean these parts on the print. So to start with, let's take the power off. We're going to de-energize the panel. Apply a lock and a tag. To make the panel safe. I'm going to test this before I touch it using a tick tracer type tester. Note that the tick tracer type tester here won't detect DC, so I'm making my test for power on the AC portions. Okay. First part that we're going to identify on the panel is the control transformer. This is the control transformer, and on the print this illustrates the control transformer. Note that this is a step-up transformer. It can be used in either way, but in this application we're stepping up from 120 volts to 240. Control transformer. The next panel the next part in the circuit is the rectifier here, and on the schematic it's here. It's the rectifier. This is the point where we change the AC power supplied to DC. From there we go to fuses. There's a positive fuse and a negative fuse. On the print, positive fuse and negative fuse. We have a stop switch. It's a normally closed momentary switch, push button. That's here. We have a start switch, normally open, momentary switch. That's here. Next thing on the drawing is an M1 mercury tube. M1 refers to the contactor that it's located on. That is a normally open, instantly closed mercury tube. We have a mercury overload relay, OL1. This is the tube for that. It's normally closed, instantly open. We have a 1A mercury tube. The 1A mercury tube. Note the difference on the symbol, the two little like wings on the side. Those designate that as a normally open, timed closing mercury tube. And I have an M2 mercury tube, which is also normally open, time closed. Right there. These are very old type timers, but they're pretty reliable actually. They're not used much anymore, but they arrange for the proper sequence of contactor closing. Next on the drawing are 2A, 1A, M1, M2 coils. The apprentice can see these. These are red in the back. These are the coils. The control circuit, when energized, causes the coil to become energized and is an electromagnet and pulls the contact tips together. The print is broken up into two parts. You have a control section and you have a power section. This section here is the power section. You'll note a lot of the same letters, like M1 contacts and an M1 coil, an M1 mercury tube. All those components are located here. The M1 contacts connect the back of the contactor to the front of the contactor through the movable portion of the contact. The M1 coil, it's the actuator. When you energize the coil, it makes a magnet to pull the contact tips together. And the M1 mercury tube, it's an auxiliary device, also operated by the coil. When the coil pulls in, there's a little arm that transfers magnetism from the coil to pull mercury and make these contacts right here. Everything labeled M1 is controlled by the M1 contactor, by the M1 coil. You have the OL1. We have an OL1 mercury tube. This is the coil for OL1. It's the bottom portion of this, the heavy wiring, the power wiring. Next we have the field, shunt field. That would be part of a motor, part of a DC motor. And it operates, or its function on the DC motor is to limit the tachometer speed, the revolutions per minute of the motor. A regular series type motor would run away without a load, would overspeed to the point of destruction. The shunt field operates to limit the RPMs. And on the panel, we don't have a motor here. We're using these lights here to symbolize a motor, and the shunt field is illustrated by this light here. When it's lit, it's as if the shunt field were powered on a motor. We'll have the armature of the motor. That's by this light. And then we have two resistors. Actually, that would be one resistor with 3 connection points on it. The center point would half that resistor. From R1 to R2 would be one resistance. From R2 to R3 would be another. And these are illustrated by these starting resistor lights here and here. Now, we can take part of the resistor away by closing the 1A contactor. That's this one here. When this contactor closed, as with the drawing, it shunts this resistance. It gives it a path around it instead of through it. Electricity will take the path of least resistance. The contactor poses a much smaller opposition to the flow of current than this resistor, so it would choose that path. And the resistor drops voltage. While with the path around it, you would have no voltage drop. And the motor would see more light, or more voltage, and the light would become brighter. The second resistor, R2 to R3, here, can also be shunted by a contact, 2A. That's this contactor. When it closes, it offers a path of low resistance, not much opposition to the flow of current, and it takes away the voltage drop imposed by this branch. And the armature light would become brighter, and the motor would see more voltage and would run faster. The M2 contactor, that's this one. The M1 and M2 are commonly referred to as master contactors. As you can see, the M1 is on the positive side of the circuit. It's thought to be the positive contactor, and the M2 is the negative contactor. And they close simultaneously. As you can see, when the control power is applied, M1 and M2 close at the same time. These two go in at the same time. One provides a connection for the motor to negative, the other one to positive. And the sequence starting at a reduced voltage first when it goes through both resistances, and then when 1A closes, it drops this resistance and it goes slightly faster. The light will burn slightly brighter. And when 2A closes, it goes faster yet, has more power, and the armature light will get brighter, or its very brightest. The proper sequence of these lights, when you initially start the panel, just as if you were starting a motor, all 4 lights would burn. The shunt field light, because it is alone, it's in parallel to the rest of the motor, would burn very bright, while these other 3 lights would burn dimly. When the M2 mercury tube, which is a timed mercury tube, times out and applies power to the 1A coil, M2 mercury tube, 1A coil. When it times out, 1A will close. This coil will get power, these tips will be brought together, and this part of the resistance is shunted out. It has a path around it. Well, the 1A light will go off. From R1 to R2 symbolizes the 1A, or the starting resistor light controlled by 1A. This light will go off. These two become brighter. When 1A mercury tube times, it has magnetism transferred by this little lever to the bottom of the mercury tube, and after the interval passes, contact is made, 2A coil receives power. This coil here receives power. Its contact tips are closed right here. When 2A contact tips are closed, the current has a path around that resistance and no longer has to pass through the resistance from R2 to R3. This light will go off. This light will become very bright as the shunt field light. And the motor's running at full speed. You can see on the drawing, it's illustrated, you have a parallel circuit with a shunt field and the armature, 2 resistors. Now, the power is the same on all branches of a parallel circuit, so this circuit has the full voltage, and on this side the voltage is shared by 3 appliances, 2 resistors and the armature of the motor and the series field of the motor. Well, these are the 2 resistors, or the components that we use to illustrate the 2 resistors, and this is the armature. As the control steps through its sequence, you drop a resistor. Now the available power is only shared by 2 components. And as we proceed through the circuit, the 2A closes, takes away this part of the load, which is here, and the armature shares its power with nothing. The shunt field and the armature are the same then, and these 2 lights will be the only 2 remaining burning, and they'll be of equal brightness. Some of this test here today, we're going to have power on. We're going to take power off several times. And prior to using these gloves, should the apprentice electrician draw problem number 2 at the testing center, this is what he'd have. When the start switch is depressed, nothing happens. No contactors close, no lights come on. Well then, let me show you proper operation first of the panel. When you depress the switch, you noted you had 3 closings. 2 of the contactors closed simultaneously, so they only made 1 click, but 3 clicks. And you had all 4 lights on. When they closed the contactors, some of the lights went off, some of them got brighter. And that's normal operation. But with this problem installed, problem number 2, if that switch is toggled, you press the start switch, nothing happens. Okay. Well, let's take the power off. We're going to lock and tag. Power's disconnected. Let's test it. Sometimes you'll get a chirp when you move the voltage detector suddenly. That's not indicative of power being on the circuit. Power's on, it chirps nonstop. It's safe to remove our gloves now. Nothing happened when we pushed the start switch. We'll begin at the beginning of the circuit. I'm going to attach my black meter probe after calibration to the positive side of the rectifier. I'm going to attach it right there. And I'm going to proceed to follow the control circuit in its entirety. First point from the positive of the rectifier, it shows to the L positive point on the drawing, which is the top front of the M1 starter. And as you can see by the meter, we have continuity. It's good. The next point, as you see on the print, is the line side of the positive fuse, and it's good. I'm going to proceed to the load side of the positive fuse, and it's good. And I'm going to go to the line side of the start switch, which is good. I make several references to line and load. The line side is toward the source. The part of any component that is toward the source is the line side. The load side is toward the work. The work meaning the conversion of the electricity to something else. In this case, on this part of the circuit, we're converting electricity into magnetism. So the load side is toward the work. That's here. All right. The next point on the print would be the top of the M1 mercury tube. And it's good. After that, we go to the bottom of the M1 mercury tube. The print illustrates this as being a normally open device, and as you can see by the meter, it is open. I'm going to test the start switch by depressing it while my meter lead is attached to the bottom of the M1 mercury tube, and I should have a circuit. The wiring is intact, and it is. Now, to remain attached to the positive side of the rectifier, I'm going to complete the rest of this troubleshooting on this side by holding the start switch in the depressed position. The next point is OL1, the mercury tube on top of OL1, and we have a circuit. That is the line side of that device. The load side is the bottom of OL1. And there you have it. To complete the rest of the positive side, go to the line side of the 1A mercury tube. It's listed as a normally open device. I'm going to check it to make sure that it is, and it is. Then the line side of the M2 mercury tube. And it's good. Again, it's supposed to be normally open. I'll check it, and it is. Then the positive side of the M1 contactor coil, and it's good. The positive side of the M2 contactor coil, and it's good. Okay. With the note that this is the first time I have to move my negative meter lead probe. I'm going to check now this short wire here from the load side of the 1A mercury tube to 2A. Positive of 2A coil, and it's good. From the load side of the M2 mercury tube to 1A coil, and it's good. And we've completely checked the positive side of the control circuit. Finding no error, let's proceed to the negative side. I'm going to attach at the source, at the negative source right here. First point it goes to is the top front of M2 starter to here, and we're good. The next point would be the line side of the positive fuse. Uh-oh, we don't have a circuit. Let's test our meter. The meter's reading, we don't have a circuit. To further isolate that, the wire shown on the drawing from the top front of M2 to the line side of the fuse, I'm going to move my probe to that point. No circuit. There you have it. This problem, we have an open wire from the top front of M2, this point here. The wire between the top front of M2 contactor to the line side of the negative fuse is open, right there. And that's that. Should the apprentice draw problem card number 3 for testing, it would read as follows. When the start switch is depressed, all contactors close. The shunt field light is the only light burning. The armature light and both resistance lights remain off. All of the control circuit is intact or the contactors would not close. Okay, let's show normal operation of the panel first. I'm going to don the low and medium gloves here and press the start switch. Click, click, click. Note the pattern of the lights. Okay. Now with toggle switch number 3 on, this is what we'd have. Wow. All the contactors are going, but the only part of the circuit energized is the shunt field. On our drawing, this is the only part of the circuit that's energized, the shunt field. This entire half of the circuit is not energized. By the fact the control circuit is operating, that tells us, you know, the contactors all closed, they all closed in proper order. That tells us that this portion of the print, this portion of the circuit is good. Our problem lies from between this point and this point. So let's stop the panel, take the power off and lock and tag. Test to make sure that our power is indeed off. We're going to turn on our tracer. This is the incoming part of the power. This is on the secondary of the transformer. It's to be noted that ordinarily these tracers don't detect DC, but it will occasionally chirp on this panel. Take our gloves off. Now, By the symptoms exhibited, we know that this part is working. This part is working, okay? But we have a problem. Our problem lies from here to here, somewhere in that area, but we don't know where. We can narrow it down further. If the problem were in the resistance, when the 1A contactor closes, it takes away this portion of the resistor. This to here is gone. When 2A closes, it takes away this portion. And the problem still existed after these two contactors closed, so we're fairly sure it's not here. Let's begin our testing starting at OL1, and we're going to test from OL1 through the armature portion of the circuit. So I'm going to hold one test lead on OL1 right here and test 2 S1A1, and it's good. That's this point here from OL1, where I attached OL1 to S1A1, and that's good. Now I'm going to test from S1A1 to the armature, and that's good. So we're fairly confident that our circuit's intact from here to here. I'm going to resume my testing at A2, from A2 right there to R1. R1 on the contactors here. Uh-oh. I have an A2 post I can refer to as well. It's not there. From the armature to A2. It's not there. I believe that's our problem. I'm going to attach my probes to A2 and have the switch toggled. And let's see if that brings the meter up. There you have it. The apprentice would mark an X on the print there and say that have an open A2 lead. Armature lead number 2 is open. That's our problem. That's that. Should the apprentice electrician draw problem number 4 at the testing center, this is what he would have. When the start switch is depressed, nothing happens. No contactors close, no lights come on. Well, we'll begin by showing you normal operation of the panel, then we'll install the problem. I'm going to put the gloves on. These testing panels, like panels underground, have a lot of exposed conductors. Much of this surface here is energized at all times. It powers on the panel. Good practice to have the gloves on. That's normal operation. You note 3 clicks, M1 and M2 go in simultaneously, then 1A, and then 2A. Note the pattern of the lights. All 4, and then these 2 go out. As these 2 go out, this one gets brighter. With each closing of a resistance contactor, we lose a light on the bottom and the armature light gets brighter. One more time, note the lights. All right. Now, with the toggle switch number 4 thrown, the problem be installed, here we have it. Nothing happens. Must be a bad commencer. It should commence when you throw that switch. Take the power off. Tag in the lock. The key in your pocket. Remember, without the key being stowed, taken with you, that lock is just a latch. Now I'm going to test this before I touch it. I'm going to use a tick tracer. You'll get the occasional chirp, you know, from a rapid movement of the instrument. But if you would really encounter power, it would be a steady alarm. I'll show you that with the extension cord. This is with power on. You can hear the tone, see the light constant. Okay, I believe we've proven power's off. I'm going to take the gloves away now. We're going to start our test. With nothing working, you don't have a clue. You don't know where the problem might lie, so the best place to start is at the beginning. I'm going to start at the positive side of the circuit. I'm going to attach my meter probe to the positive post of the rectifier. The first test I make, I attached a probe right here. The first test I'll make is to the top front of the M1 starter, top front, and that's here. Note the meter reading. We have a good circuit. The next point that goes to is from here, to the line side of the positive fuse. Well then, we don't have a circuit. Let's pinpoint that a bit farther. We'll remove the lead and test only the wire we suspect. We'll go from the top front of M1 to the line side of the positive fuse, and I have no circuit. So the apprentice could mark his print in the test right here and list that as wire open from top front of M1 contactor to line side of positive fuse. That's that. Should the apprentice electrician draw problem number 5, this is what he'd have. When the start switch is depressed, nothing happens. No contactors close, no lights come on. That reads the same as problem number 4, but it'll be a different problem. Let's show you normal operation of the panel again. We're going to put our gloves on. I'm going to press the start switch. Click, click, click. And note the pattern of the lights. There's 4 starters here, but M1 and M2 close simultaneously, so you only hear 1 click for those 2. And they all open at once. Okay, with toggle switch number 5 thrown, this is your problem. Push the start switch, nothing happens. Okay, let's make the panel safe by disconnecting the power. We're going to lock and tag. Put the key in your pocket. Now, although we've disconnected it, we're still going to test this with a voltage tester. You'll get the occasional chirp from moving the tester too quickly. That's not indicative of power on a circuit. When you have power, it chirps non-stop. After we've determined the power is off, we can take the gloves away. With nothing operating, nothing on the circuit works, you don't know. it could be any part of the control. Nothing works. So we'll start at the beginning, which is always a good place to start, is at the beginning. I'm going to attach one of my meter leads to the positive of the rectifier, and I'm going to proceed in a line-by-line fashion until we find our problem. On my first test, I don't have a problem. Let's check our meter. Now, our meter's functioning, but the first point that we go to from the rectifier to the top front of M1 starter, there's no circuit. And that's our problem. We have an open wire from the positive terminal of the rectifier to the top front of M1. Be an open wire. That's that. Should the apprentice electrician draw problem card number 6 at the testing center, this is what he'd have. When the start switch is depressed, nothing happens. No contactors close, no lights come on. Well, we've heard that before, haven't we? Although the problem's expressed the same, on the board it'll be greatly different. Let's put our gloves on. Show you normal operation first. Click, click, click. You have 4 contactors, but you'll note you only have 3 clicks because M1 and M2 close simultaneously, then 1A and then 2A. All 4 lights light up first, and these 3 are dim, and R1, R2 light will go off. These 2 will become brighter. R2 and R3 will go off, and this one will be very bright. Watch close. Watch the lights. Okay. Now with the problem installed, toggle switch number 6 is thrown on the back of the panel. You depress the start switch and nothing happens. Okay, let's remove the power. We're going to lock and tag. Don't forget to take the key from the lock. I'm going to use the tick tracer here to make sure that we have no power. Okay. I believe it'll be safe now to remove the gloves. With nothing happening, none of the control circuit operates. You don't know where the problem may lie. None of the control circuit works. So the obvious place to start your test is at the beginning of the circuit. We'll start at the rectifier. I'm going to attach my black meter lead with alligator clip to the positive terminal of the rectifier. And the first place to test to, the first wire, would be the top front of the M1 starter to there. And if you'll refer to the meter, you'll see that we have a circuit. We have continuity on that wire. It's to be noted, you probably already realized, that these problems are installed with toggle switches. Now, you're limited to what sort of problem you can have with a toggle switch. You could have an open by putting a toggle switch here. If you open that, there's no circuit. You'd find no continuity with the meter. If one of your components is supposed to be open, you could put a toggle switch across that, and when you operated the toggle switch, it would be shorted, and that would do. But you can't use a toggle switch to cause a coil to be open. You can only open the wires going to the coils. You can't cause a rectifier to fail with a toggle switch. You could just show an open to the rectifier or away from the rectifier. Same way with you can't really break a resistor with a toggle, but you can, the wires that connect the resistor to the circuit, you can open. Now, to resume, our first test was top front of M1, and it was good. The next point that we test, the line side of the positive fuse, and it's good. Let's test through the fuse. If the fuse has continuity, we'll read it here, and it is good. The next point, line side of the stop switch, and it's good. The stop switch is normally closed. It's a momentary push button. So we're going to read to load side of the stop switch, and it's good. That's reading across. Now note, I've attached one meter probe to the positive terminal, and I'm progressing in a linear fashion, going from point to point to point. And that's much easier to keep track of where you are in the circuit. Should the apprentice electrician draw problem card number 7, this is what he'd have. When the start switch is depressed, M1 and M2 contactors close immediately. The shunt field light comes on when M1 and M2 contactors close. No other light comes on until 1A contactor closes. Then the armature light and the bottom right resistance light come on dimly. When 2A contactor closes, the armature light turns bright. Well, let's glove up here and put our panel through the paces and show them normal operation to have everyone refreshed on that. Normal operation is as follows. Press the start switch, click, click, click. You'll note you have 4 lights. Note the pattern of the lights. You have the shunt field light bright, the other 3 are dim, and then the second click you hear, this light goes off. These 2 get brighter. The third and final click, this light goes off. This one is very bright. Watch the lights. And there you have it. Now with toggle switch number 7 thrown, we're going to install a problem. You press the start switch. We still had the 3 clicks. All of our contactors closed as they should. But pattern of the lights is wrong. Now note, the lights indicate a motor action. Should we be controlling a motor with this starter instead of the lights? When you first started, the motor would start at a slow speed, and then very shortly after would speed up slightly, and then at a short time interval later go at full speed. And the armature would be dim, that's slow, slightly brighter, slightly faster, and then full brightness, full speed. With this problem, on the first click, we don't move at all. The second click, we're going to start with a lurch. And instead of having a 3-step acceleration, we only have 2. First movement, none at all. And then start with a lurch. and then go to normal operation after the second click. Well then, let's take our power off and lock and tag. I'm going to stop it. It's to be noted that the lock and tag operation's a good deal easier here in training than it is in real life. It takes a good deal of discipline to do this correctly if you have to walk a couple of 100 feet, sometimes in poor conditions, bent over or in wet conditions, to go take a cat head out of the power source and apply a lock and tag and then go back to your work. But that discipline's necessary to stay safe, stay healthy. After the power's been removed, I took my gloves off too soon there. Slide those back on. To make sure that it's been removed, I'm going to test it before I touch anything here. And I believe we're fairly sure the power's off. If you think back to the operation of this panel with the problem, all of the control circuit operated. When the contactors close, the control's done its job. Click, click, click. M1 and M2 went in, 1A went in, 2A went in. Should the apprentice electrician draw a problem card number 8 when he goes to the testing center, this is what he'll have. When the start switch is depressed, M2 contactor closes, M1 contactor remains open. No motor lights are working. If the start switch is held in, 1A and 2A contactors will close, but there's no holding circuit. When the start switch is released, all the contactors open. Okay, let's show you a normal operation first so it'll be easier to detect the problem. We'll put our gloves on. Lots of energized stuff on this panel. It'd be easy to bump into something bad there. I'm going to push the start switch. And there you have it. 3 clicks. M1 and M2 close simultaneously. 1A, 2A. That's the normal sequence. The lights, all 4 lights immediately light up, but only one is bright. 3 are dim. When 1A closes, the left-hand bottom light goes off, the right-hand bottom and the right-hand top get brighter. 2A closes, the right-hand bottom light goes off, and the right-hand top light gets very bright. That's normal. Watch closely and let's see, can we pick up on what's happening here. And there you have it. Click, click, click. Now, if we're going to stop it, toggle switch number 8. And this is the panel with the problem installed. Let's see what happens. I heard 3 clicks. No lights though. And when I released the start switch, it stopped. That tells you have no holding circuit. These are momentary switches. They're only made or broken as long as you hold them in. So you're dependent upon part of the circuit to give you a holding circuit. Holding circuit means it'll keep the contactors closed and allow you to turn loose the switch. But we don't have that. Nor do we have any power to any portion of the motor. Okay, let's take the power off, lock and tag. We can test for power after we've locked and tagged. I'm using our tick tracer type voltage detector. You'll get the occasional chirp caused by moving too fast. That's not indicative of any power. It's a constant chirp, and I'll flash the light when you have power. It won't show anything. I believe we're safe. Let's take our gloves off. When we operated the panel with the problem on it, we noticed that had no lights operating, as well as no holding circuit. The holding circuit is dependent upon M1 mercury tube. M1 mercury tube must operate to allow you to turn loose the start switch. If M1 mercury tube doesn't close, then you'd lose power as soon as you released the start switch. When you press it, put power to M1 coil, you have a circuit, M1 mercury tube closes, you can turn loose the start switch and you have a path around. It's a bypass circuit through the mercury switch instead of the start switch. Well, that's not happening. As a matter of fact, none of the jobs that M1 done is happening. This contactor's not closing. We heard 3 clicks. M1 and M2 is supposed to start simultaneously, then 1A, then 2A. But if you were observing, you'll notice M1 didn't close. M2 closed, 1A, 2A. M1 didn't close. When this doesn't close, the positive side of the rectifier is not connected to the motor. If the contactor doesn't close, it's a control problem. So we're going to check the control portion of the print, particularly with M1. By the closing of these contactors, 2A, 1A, and M2, we can be reasonably certain that all this is intact. Now, problems lies between here and here. Let's check that. We'll begin at the load side of the OL1 mercury tube and check to the positive of the M1 contactor. And check to the positive of the M1 contactor coil. And we have it. So that part of the circuit's good. From here to here is good. So let's check from the negative of M1 to the load side of the negative fuse. That's a good deal easier to reach, this portion. And we don't have it. Let's test our meter just to make sure the meter's good before we call it. The meter's reading correctly. According to the drawing, I should have a circuit from the negative of this contactor coil to the load side of the negative fuse. It's not there. To further check it, let's check another contactor just to make sure. From the negative of the 1A contactor to the load side of the negative fuse reads good, but not from M1. The trainee could say this wire from the negative side of the M1 coil to the load side of the negative fuse, load side being the side toward the work, line sides toward the source, load side of the fuse to the negative side of M1 coil. This wire is open. There you have it. Should the apprentice draw problem 9 at the testing center, this is what he'd have. When the start switch is depressed, all the contactors cycle in normally. All the lights, with the exception of the shunt field light, operate normally. The shunt field light doesn't work. Okay. Well, before we could really understand the problem, let's watch the normal operation first. I'm going to glove up here. Lots of hot stuff on this particular trainer. If it's energized, you need your gloves. There you have it. Note, M1 and M2 close simultaneously, 1A, 2A. At the first closing, all 4 lights burn. The shunt field light, the armature light, and both starting resistors. Now the armature and the starting resistors are dim because they share one branch of that parallel circuit. Now, when 1A closes, this starting resistor light goes out. It's bypassed. These two get brighter. When 2A closes, this starting resistor light goes out, and the armature is very bright, same as the shunt field. Now let's install the problem. Let's toggle the switch. As the problem stated, all the control works normally. They all close in proper sequence, and they hold. You can turn loose the start switch, but the shunt field doesn't light up. And the control operates correctly. You have M1 and M2 going in simultaneously, 1A and 2A, proper order. These 3 lights came on dim. When 1A closed, the R1, R2 light went off. When 2A closed, the R2, R3 light went off, and the armature is very bright. The only part of the circuit that didn't work is the shunt field. Now this is a problem that could exist in real life on a real motor. You could have a shunt field open, not operating, and the motor would still run. You would not have speed control though. A shunt field in a compound motor causes the motor to operate at a certain RPM and be reasonably stable at that speed. Without the shunt field, this would be a regular series motor, and a series motor doesn't offer good speed control. And as a matter of fact, without a load, a series motor will accelerate to the point of destruction. It'll throw itself apart. So, our problem is with the shunt field branch. Looking at the drawing, this portion of the panel is operating correctly. The control portion of the panel is operating correctly. The only part that's not operating is from here to here, this particular branch. So let's take our power off, lock and tag. With a voltage tester, let's check and see that power is indeed off. You'll have a little nuisance chirp, but if you have power, it locks on, it stays on. You'll be able to tell the difference pretty quickly. Let's show that. That's power. This little chirp. I believe we're safe here. So we're going to take the gloves off. As we illustrated earlier, we feel that our problem lies on only one part of the circuit, from here to here. And that F2, S2 point on OL1, that's this point right here. It should read little or no resistance from here to there. And if we have it there, this point here, the F1 point, should read little or no resistance from here to M2, right here in the back. Let's check those places. The first point, overload relay to the shunt field light. We don't have a circuit there. Let's test our meter. We zeroed this meter earlier, but sometimes they need a little touching up. Like now, we're going to touch this one up to re-zero it. And we're confident our meter is operating correctly. Check from here to here. No circuit. Well, just for curiosity's sake, let's check the other side of that circuit. From there to here. So, it shows intact. That tells us that we're open from this point, F2, S2, here, here, to there. Here to here is open. This part of the circuit, this part of the shunt field, from here to here is good. That's from this side to that side. It's good. So the apprentice could note on his print, he could put an X here, and label that with the number of the problem, and to write his problem, he could say shunt field open from the load side of OL1 to the shunt field. F2 lead open. That's that. If the apprentice electrician should draw problem number 10 at the testing center, this is what he would hear. When the start switch is depressed, M1 and M2 contactors close immediately. A holding circuit is achieved. The shunt field light comes on bright, the armature light, the bottom left resistor light, the bottom right resistor light comes on dimly. 1A contactor and 2A contactor do not close. Well, let's glove up. And we're going to operate the panel for normal operation, show you what it should be doing. You heard the 3 clicks. M1 and M2 close simultaneously. And after an interval, 1A closes. Then after another interval, 2A closes. The light pattern, normal operation, we'll initially start the panel. All 4 lights come on. These 3, the bottom 2 resistor lights and the armature light, are dim. After the second click, when 1A closes, this starting resistor light goes off. These other 2 get brighter. Third click, when 2A closes, the bottom right light goes off and the armature light is at full brightness, the same as the shunt field. That's normal operation. Watch the lights. And there you have it. But our problem states something somewhat different. If we'll toggle switch number 10, I'll show you the problem. You depress the start switch. And the normal progression of the panel through the cycle is interrupted. M1 and M2 close. 1A doesn't close, neither does 2A. We stay in the first step of operation. If this were on a piece of equipment, you'd only have low speed. Do it one more time. Okay, let's take the power off, lock and tag. Put the key in her pocket there. Want to test the panel, make sure that we have no power. No power is evident. I believe we're safe to remove our gloves. As we've illustrated in earlier problems, when you depress the start switch, you complete a circuit to allow the power to flow through M1 and M2 first. These two operate. That's this and this. When they close, they allow power to go to the motor part of the circuit. This is the control part. This is the motor part of the circuit. Well, when the M1 and M2 close, the master contactors, the M1's for positive, M2's for negative, then you complete this part of the circuit. The shunt field light is on a separate branch. It's immediately at full power. The armature, the light between R1 and R2, the first stage resistance, and the second stage, share this branch. And with the power being divided between 3 loads, these 3 lights are dim. Armature, the light between R1 and R2, light between R2 and R3. We can refer to them as the 1A resistor or the 2A, and that would make it easier to reference. When 1A closes, it bypasses that resistor. That causes that light to go off. It takes away that part of the voltage drop, so this light for the 2A resistor and the armature will get brighter. When 2A times and closes, it bypasses this section of the... Should the apprentice electrician draw problem number 11 at the testing center, he would hear this. When the start switch is depressed, M1 and M2 contactors close immediately. A holding circuit is achieved. The shunt field light comes on bright. The armature light, the bottom left light, and the bottom right light doesn't come on at all. After 1 second, the 1A contactor goes in. The lights still do not come on. After another second, the 2A contactor comes in, and the armature light comes on at full brightness. Let's glove up, and we'll show how that problem looks. We'll do normal operation first. To remind everyone of what we're supposed to see. You had the M1 and M2 closing simultaneously. After 1 second, 1A closes. After another second, 2A closes. The shunt field light very bright. All 3 of the others dim. When 1A closes, this light goes off. These 2 are brighter. When 2A closes, this light goes off. The armature is very bright. One more time. Watch this closely. Watch the lights. Okay. Now we're going to toggle the problem in, problem number 11. And when we depress the start switch, you'll note that we had the 3 clicks. The contactors all closed in the normal sequence. The first click, M1 and M2 closed. Second click, 1A closed. And on the third click, 2A closed. But our lights illustrated a problem. We didn't have power where we were supposed to. M1 and M2 closed, only the shunt field was lit. All 4 lights should be lit, 1 bright and 3 dim, but only the shunt field was lit. When the second contactor closed, when 1A went in, there was no change. When the third contactor closed, 2A closed, the armature light come on very bright. If this were on a motor, on a piece of equipment, say it was a traction motor, when the operator depressed the tram pedal to go, nothing would happen. He would hear the clicks in the panel. And then when it cycled through the control to the high speed, then the piece of equipment would start with a lurch. It would jerk from 0 to high tram. Okay, let's watch it one more time with the problem, and then we'll take the power off and check it out. Okay, I'm going to disconnect the power here. Lock this circuit out. Now we're going to take our voltage detector and see if we can find some power. And we don't have any. All is well. You have the occasional chirp from the instrument there from moving it too rapidly. But when you encounter an energized circuit, it alarms with a solid alarm. It's safe to take the gloves off now to troubleshoot this. Before we apply our instrument though, let's talk. Now, this part of the circuit here is the control circuit. These, the switches and the coils, bring about an action to close the contactors. And when the contactors close, they put the power to the motor, through the starting resistors and to the motor. That's where our problem lies. The control is all operating as it should. This part is doing well. There's no use to spend a lot of time checking the control when it's operating correctly. But this part of the circuit is not functioning correctly. Ideally, when M1 and M2 close, the main contactors, positive and negative, you should have a circuit that would energize the shunt field, the armature, the resistor between R1 and R2, the resistor between R2 and R3. Then after an interval, 1 second, 1A close. This light would go off, this one would be brighter, and this one would be brighter. After 1 second, 2A would close. This light would go off. The armature would be very bright. The shunt field and the armature would be the same intensity, the same brightness, and have the same power on them. What we have happening though, we don't have a complete circuit here at all until 2A closes. That would indicate that the circuit will not operate with the resistor between R2 and R3 in the circuit. When 2A closes and bypasses that part of the resistance, the armature is finally energized. Okay, let's check that part first, see if a problem does indeed lie there. According to our diagram, one side of that resistance goes to the front of 2A, the other side of the resistance goes to the rear of 2A. Now for training purposes, I've labeled these points for the apprentices here to learn the panel. That the panel you test on may indeed not be labeled as such, but you can figure it out because you have an instrument and you have a map, you have a print. So let's check this out here. I'm going to disregard the labels and just check this as if we don't know where it's supposed to be. I'm going to try to determine which side of this light is connected to which side of the contactor. I'm going from the R2 on the light. I'm going to ignore this label and see if it's to the back. It's not. So let's check the front. Hey, there it is. So we've oriented ourselves now. We know where we're at. If the left side of that resistance connects to the front of this contactor, by that we know that the right side of the resistance is to be connected to the rear of the contactor. But there's no reading. We're sure our meter is right, it's calibrated. We know that that's one side of the circuit. By default, this must be the other. It does not read. The apprentice could illustrate this problem on the print. I'm making an X right here. And he could write the answer to the problem as starting resistance open between R2 and R3. There you have it. Should the apprentice electrician draw problem number 12 for testing, he'd receive this one. When the start switch is depressed, M1 and M2 contactors close immediately. When the start switch is released, contactors fall out. There's no holding circuit. Let's show you normal operation of the panel, what should happen. And then we'll install the problem by operating a toggle. Here we go. Watch the lights. You'll note when we start, you hear 3 clicks. M1 and M2 close simultaneously. Then after a 1 second interval, 1A closes. After a 1 second interval, 2A closes. With those closures, the lights change. On the first click, all 4 lights come on. 3 of these lights will be dim. 1 is bright. The shunt field light is bright. The 2 resistance light and the armature light is dim. First second passes, 1A closes. This light on the left, on the bottom left, will go out. These other 2 will get brighter. After another 1 second interval, 2A contactor closes. When it closes, the bottom right light goes out and the armature gets very bright, same as the shunt field. That would be top speed on the motor. With the problem installed, this is what you see. Here we are. We press the start switch. All the contactors closed as normal. But as soon as I release the start switch, they fall out. Note that as discussed earlier in the problems, we have momentary switches. They're not like switches such as a light switch in your home where you would flip the switch and it would remain in a closed position. These switches return to their normal status as soon as you release them. It's a momentary switch. Let's take the power off and lock and tag, and then test this with the instrument. Okay, we've taken the power off. I'm going to take this voltage detector These voltage detectors are very sensitive. They've got a wide range from 50 volts to 1,000 volts AC as it's listing. I believe it'll pick up a somewhat smaller voltage than that, and it does respond to sudden movements. Now, it's not recognized as a DC tester because DC doesn't have the necessary relative motion to operate this. But with this panel, we're powered with an AC power supply going to a rectifier, and it will detect this particular kind of DC. It's a chopped DC, and then it will detect it. We've established that the source power is off and the panel is safe to test. Now, we spoke of the holding circuit. The holding circuit is part of the control that's in this portion of the print. As you can see, the components involved, there are two components, the start switch and the M1 mercury tube. The holding circuit is made up of those. The M1 mercury tube is actuated as an auxiliary device on the M1 contactor coil. When the M1 contactor coil is energized, when it's energized, it becomes a magnet, and it has the effect of closing these contactor tips, supplying positive voltage to this part of the circuit over here. And also, the magnetism is responsible for closing this mercury tube. A mercury tube is one of the first relays that were used, and a mercury tube has mercury in it. Mercury does respond to magnetism. It's a liquid metal, and you can use it as a timer by the magnetism drawing the mercury through various size orifices, openings to fill a vessel and close a circuit between two contacts. This one, though, is not a timed circuit. It's an instantaneous. It's normally open and instantly closed. As soon as this coil is energized, magnetized, this little bar bolted onto the side of the movable portion of the contactor transfers that magnetic energy to the mercury tube, draws the mercury inside the tube into the contacts, and completes the circuit. Well, that may indeed be happening, but for whatever reason, it's not completing the circuit. Now, with the mercury tube and power off, all we can check on it is its normal status, whether it's normally open or normally closed. The print says it should be open, and indeed it reads open. So at this point in our testing, that's as far as we can go with testing of the tube. The other part of the circuit that's involved here is wire. There's a wire that connects the line side of the start switch to the top of the mercury tube. We can test that wire for continuity. the line side of the start switch to the top of the mercury tube. We should have a circuit there, and the meter indicates there is no circuit. We're going to test our meter just to be sure. And there is no circuit there. Well, while we're here, let's just check the other side of that mercury switch. We're going to test the load side of the start switch. On the print, that would be here, to the load side of the mercury tube, which is the bottom of the mercury tube. That part of the circuit, as the meter indicates, is intact. Line side of the start switch to the line side of the mercury tube. The wire between, the wire connecting these components, is open. So the apprentice could list this problem as an open wire from the line side of the start switch to the line side of the M1 mercury tube. He could mark it on his print for testing with an X right there. And that's that. Should the apprentice electrician draw problem card number 13 on his test, it'll read as follows. When the start switch is depressed, M1, M2, and 1A contactors close immediately. The shunt field light comes on immediately, and the armature light and the bottom right resistor light come on dimly. After 1 second, the 2A contactor closes and the bottom right resistor light goes out. We're going to show a normal operation of the panel first. We'll put our gloves on. So a lot of these components on this trainer here are energized whenever the panel has power on it. Here we go. For normal operation. You press the start switch, you hear 3 clicks. M1 and M2 go in simultaneously. After 1 second, 1A goes in. After another second, 2A goes in. The effect of that with the power lights, the indicator lights, when first energized, the shunt field light is very bright. These 2 resistor lights on the bottom are dim, and the armature light is dim. After the 1A contactor closes, the bottom left resistor light goes out. The other 2 become brighter. After the 2A light closes, or the 2A contactor closes, the bottom right light goes out, and this light is very bright for the armature. Watch the lights and listen to the contactors. We'll try it one more time. There you have it. That's correct operation. Now we're going to toggle switch number 13. And this is with the problem installed. This will be in malfunction. A couple of things you should have noticed there right off the bat. I only had 2 clicks. All the contactors are in, so that would tell you or cause you to think that the timing is off. The timing sequence is off. We closed all the contactors, but we closed either 2 at a time twice or 3 at a time and then 1 by itself. The lights. The bottom left light never came on at all. The bottom right was dim. The top right was dim. The top left was bright. It performed normally. After 1 second, we had a contactor closed, 2A closed, and the bottom right light went off. That's normal for the 2A to close and the bottom right light to go off. Our malfunction was 1A contactor went in out of sequence. It went in at the same time as M1, M2, when we first started. That was illustrated in the written portion of the problem. M1, M2, and 1A closed immediately. There should be a 1-second time delay provided for 1A contactor by the M2 mercury tube. That component's function is to time 1A start. So let's look at it in operation one more time. Part of our holding circuit, or part of our control circuit, didn't operate. The timer for 1A didn't work. It started immediately. Let's take the power off. See if we can find a problem. Take our voltage detector. Now I believe we have the power off. I believe it's safe to handle this panel now. We're going to take our gloves off. When we operated the panel, what we noted in the control portion of the print, when we close the start switch, we have a circuit through the wire to the overload mercury tube and to the top of these two mercury tubes to the M1 coil and the M2 coil. Through these devices to the negative fuse and completing the circuit back to the rectifier. Now you'll note that there is nothing to limit this control power to M1 and M2. They're to be energized and operate immediately when you close the start switch. Okay, note also that there's a timing device, a timing mercury tube on 1A's circuit and 2A's coil circuit. The 1A coil is timed by a mercury tube attached as an auxiliary to the M2 contactor. When M2 becomes a magnet, it has the effect of closing these tips and providing a path for the negative for the power circuit, as well as timing this mercury tube. When the symbol on the print is shown like this with the two little outriggers on the stationary part of this, that means it's a timed mercury tube. Well, that part of the circuit's not working. It's 1A and M1 and M2 are going in at the same time, immediately. As soon as the start switch is closed, these three coils receive power and close immediately. So the part that's malfunctioned is the M2 mercury tube. It's not working. So let's check that. First thing we could check about that M2 mercury tube, let's check the wiring. Let's start from the overload relay's mercury tube. I'm going to start with the line side of the overload relay mercury tube, right here. We're going to check to the line side of the M2 mercury tube. And that part of the wiring is good. Now to check the device, the print illustrates it as normally open, timed, closed. So this should be open, should be no circuit. But indeed we have a circuit. The component has failed, it's shorted. as a short circuit. It shows continuity through the timing circuit when it should not have it. The apprentice could list this problem as the normally open, timed close M2 mercury tube has shorted. He could mark an X on that mercury tube, label it problem 13 on his print. And that's that. Should the apprentice electrician draw problem number 14 at the testing center, this is what he'll have. When the start switch is depressed, M1, M2, and 2A contactors close immediately. The shunt field light comes on immediately, and the armature light and the bottom left resistor light come on dimly. After 1 second, the 1A contactor closes and the bottom left resistor light goes out. Let's put our gloves on here and give that a go. We're going to operate it normally first to show you what normal operation looks like without the problem toggled in. There you have it. You'll note you had 3 contactor closures. You heard clicks, 3 clicks. 2 of the contactors go in simultaneously. M1, M2 go up at the same time. After 1 second, 1A goes in. It closes. After 1 second, 2A goes in and closes. The effect of that on these lights, when you initially close these 2, all 4 lights are on. The shunt field light is bright. These 2 on the bottom are dim. This one is dim. If you note on the print, the shunt field light is parallel to the armature and resistance 1 and resistance 2 lights. So they share that branch. The voltage is divided between the 3. When 1A closes, this light goes off. It's bypassed. The power goes around it where there's less opposition. The light goes off. These 2 are brighter. When 2A closes, this light goes off. It's bypassed. It goes through the contactor, goes around the resistance rather than through it. The effect of that is the armature light shares its power with nothing. It's as bright as the shunt field. The motor's at full speed. But the sequence of these contactor closings is the problem here. It was illustrated on the problem, the improper order. 2A closed at the wrong time. Watch proper operation one more time. There you have it. Click, click, click. The proper pattern of lights. Now, let's toggle the switch number 14. And with the problem installed, let's see what happens. I only heard 2 clicks. This light never came on at all. That part of the resistance symbolized by this light is controlled by this contact. Two clicks. The circuit has been abbreviated in that this contactor closed out of time. Let's lock and tag. We're going to test this circuit with a voltage detector before we start. Should the apprentice draw problem number 15 when he takes his test, this is what he'll hear. When the start switch is depressed, M1 and M2 contactors close immediately and a holding circuit is achieved. The shunt field light comes on bright. The armature light, the bottom left resistor light, and the bottom right resistor light come on dim. After 1 second, the 1A contactor closes and the bottom left light goes out. The armature and the bottom right light brighten slightly. The 2A contactor does not close. Let's power the panel up here and do a normal operation. This is what we hope to achieve after the panel is repaired. And that's normal operation. M1 and M2 go in simultaneously. After 1 second, 1A closes. After 1 more second, 2A closes. The effect of that on the lights. They all 4 come on at first. This one bright, these 3 dim. After 1 second, when 1A closes, this light goes out. These 2 get brighter. When 2A closes, this light goes out. This one is bright. These 2 are the only ones left. Watch it again. Listen for the contactor action and watch the lights. Hear 3 clicks and you see that pattern. 1 more time. Okay. Now let's install our problem. It's problem number 15. Here we go. When we start at this time, well, we noted only 2 clicks. M1 and M2 closed. Anytime you have a light at all, M1 and M2 are both closed. Then after a 1 second interval, 1A picked up, this light went off. And we're still waiting, but 2A is never closed. I don't believe it's gonna. Let's try it again. M2 and M1 closed, 1A closed, 2A never did close, stayed down. This light went off. When 1A closed, this light went off. 2A still on. This contactor didn't go in. So there you have it. If this was a motor on a piece of mining equipment, you would start and you'd have low tram, and then you'd have an intermediate speed, and it would never cross over into the highest speed. It would stay at a medium speed. Let's take the power off, lock and tag, make this panel safe, and then we'll look for the problem. We use this voltage detector. It does a little nuisance flash at times. If you make a sudden movement with it, it'll flash. But should it actually detect power, it'll be a constant light and a constant tone. Okay, fellas, we've illustrated 15 problems here, 15 different scenarios where you could find. And we've shown you the proper operation of the panel with power on it, and we've showed you the faulted panel, 15 different faults that you could press a button and note either the action or inaction of various parts of the panel and detect a problem. Now, those are all well and good, but to solve a problem in that fashion, you have to make deductions. You have to think and really truly have a keen grasp of exactly what's going on with the circuit. After weeks of training on one circuit, you'll have that grasp. But every piece of machinery that you encounter, you won't necessarily have such a grasp as that. You won't necessarily know everything that should happen in proper sequences it should happen in. And a lot of our machinery is a good deal more sophisticated than this trainer. So what I'd like to show you now is with the power off, without any clue, any preamble, anything at all to give you a head start on what the problem is, you can check every single part of this panel in a linear fashion by just following the print. And it's fairly easy to do. Regardless of where the fault would lie, you can find the problem. With a print and a meter, you can find any problem on any machine. So here we go. Starting at the power source, I'm going to zero this meter. We've moved about quite a bit. You'll note that some of these readings won't be completely zero. There is some resistance on every connection, every switch. There's a small amount, and checking in this fashion, you know, we're going to make several checks in series, and those resistances will be added. So we want to always get a full scale deflection of the needle to zero. I'm going to start here at the positive terminal. You can start on either side, it doesn't matter, but you just need to be complete. Start and follow. I've attached the probe here. First position, the top front of M1. Next position, line side of the positive fuse. Load side of the positive fuse. Line side of the stop switch. Load side of the stop switch. Line side of the start switch. Now, I don't want to pass this. I want to go ahead and check it to the line side, or the top of the M1 mercury tube. The mercury tube is to be open. It's illustrated as an open. I'm going to check to make sure that it is, and my meter indicates that it is open. Now with that, I'm going to have to lay the probe down now and depress the start switch. I'm going to hold that start switch with my thumb, go to the overload relay, the top connection on the mercury tube, and the bottom. From there, I'm going to go with the print 1A, top of the 1A mercury tube. It should be open. I'm going to check the bottom, and it is. Top of the M2 mercury tube. It should be open. Go to the bottom. It is open. The positive of the M1 starter coil. There we have it. And the positive of the M2 coil. And there we have it. We have checked the entire positive portion of the control circuit with the exception of these two small wires. They're small on the drawing, but in fact they're as long as any of the others in real life on the panel. The bottom of the 1A mercury tube to the positive of the 2A coil. Here we go. The positive of the coil. It's intact. And the bottom of the M2 mercury tube to the positive of the 1A coil. And there you have it. Had there been a problem anywhere on that circuit, if you remember the problems that we found, we had an open wire here, we had an open wire here, we had an open wire here, we had an open wire there, we had a shorted mercury tube, we had a shorted mercury tube. You know, those problems, out of the 15 that we checked, those problems become apparent after we saw the symptom, we read the problem, we saw the panel operate, and you know, through these many minutes and even hours of testing the panel, we could have found any one of those had they existed just now, in just a few minutes, with no power, no hint. Now to complete the control circuit, that's attached to the negative of the rectifier. This side of the circuit's quicker to check. There's no controls, there's no switches and stuff like that. I attached the lead right there. Let me have my pointer back here. I attached the black lead right there, clipped it on. First point it goes to, the top front of M2 contactor. That's the negative contactor, the master contactor that controls the negative for the entire motor circuit. The next point, line side of the negative fuse. Here we go. That's good. The load side of the negative fuse, right there, that's good. I like to stay in a line, do it in a proper sequence so that you don't get lost and omit a check. Negative of the 2A coil. Well then, we've got a problem. That's one of the incomplete readings I was referring to. I believe we have a dirty switch, but you can see it did make. The next point, 1A coil, negative of 1A coil. That's good. Negative of the M1 coil. It's good. And the negative of the M2 coil. That's good. And if you recall, through the problems that we talked about earlier, we had symptoms. We tried the panel with power on. We saw the malfunction exhibited in the lights. And we had an open return wire, negative wire on M2, M1, 1A, and 2A. We had an open wire from the rectifier to the top front of M1 or M2 contactor. We had all those points. Had any one of those existed, we would have found it just now. Okay, let's move on to the power portion of the print. Now, so far, we have checked to the line side of M1 and M2 as part of our power circuit. The line side of switchgear, both contactors and switches, is the stationary portion. The stationary part of these contactors is the top front connection. The rear connection goes to a shunt strap and goes to the movable part, the part you hear click in. That's the load side. Well, we've checked to the line sides. Now we're going to check the other side of the contactor. I'm going to attach my probe. Again, I want to make a connection and only manage one probe at a time and build upon those checks so that I don't omit by changing places with the leads. I'm attaching my probe here. That's this point right here. First point it goes to is this point. That's good. Then it goes here. That's these two places here. This F2, S2. You can see the two wires. Now, this is the beginning of the parallel circuit in the motor. You can take one line or the other. Routinely, I take the shunt field because it's the first one I come to. From the shunt field, F2, S2. It's good. I can also take S1A1 from this point right here, that's here, and right there to there. That's here. There's a post on this panel for your convenience to check to. And there you have it. Now, at that time, if you reach there, you've checked as far as you can go without reading through one of these light bulbs. And we could read through the light bulb. Watch the meter. When I'm going to read through this light bulb, note the extremely high resistance. Now, that could give you a distorted reading on the control wiring, which should be no resistance. If I would adjust my meter to accommodate reading through a light bulb, I would have it set